Hello and welcome to the At Odds podcast. I'm your host, Ricky. Thank you so much for joining us. Today, we've got a special podcast with Dr. Chetan Nayak from Microsoft to talk about quantum computers and their really amazing breakthroughs that they've come up with their Majorana 1. This is really, really fascinating. So let's jump right into it.
I'm Chetan Nayak. I'm a technical fellow at Microsoft. I head up the quantum hardware program. We are building a quantum computer. And quantum computer, like a classical computer, has hardware, it has firmware, it has software. There's the architecture of the quantum computer, there's the applications. So, the problem of building a quantum computer, or I should say a quantum computing system, has many facets. My main focus is the hardware and, everything it takes to make this thing a reality.
So you were working on some of this stuff even before Microsoft, is that right?
So I got my degree in physics. I have a PhD in physics from Princeton. I was a professor of physics at UCLA, about 20 years ago, a little more than 20 years ago. And I was interested in quantum computing. Actually, when I was in graduate school is when Peter Shor discovered his algorithm, Shor's algorithm. And quantum computing had existed as a concept. The concept of quantum computing goes back to early 80s. Richard Feynman, the famous physicist, first thought about quantum computing then because he was trying to understand this problem. How do you simulate quantum systems? We know nature is quantum mechanical. We want to simulate materials and chemistry. And he observed the quantum mechanical, if you look at the underlying theory, the amount of what you would need to properly simulate it is unmanageably large with any conceivable classical computer. And the only way you can do it is with a quantum computer. But that was kind of like a curiosity in the 1980s. No one took it too seriously. And then Peter Shor, the thing that he figured out is, if you had a quantum computer, which is a big if, right? Because again, nothing like that existed at that time, nothing even remotely similar. But if you have a quantum computer, you could use it for code breaking, for cracking RSA. And, at that point, of course, the government and lots of other people take notice. So then it becomes something that people say, well, we don't have this, but it's not a curiosity, because if anyone did have this, that would be a big deal, and either viewed as an opportunity or a major security flaw, and so or security threat. So that's when quantum computing really got interesting. I was, not very actively focused on it, but I was definitely working on many of the problems in solid state physics of semiconductors and superconductors and how you make devices out of these things that could be relevant, could be enabling for quantum computing. And around that time, Michael Friedman, who was at Microsoft, read some of my papers and came to my office one day and said, "Hey, I think what you're working on could be useful for making a quantum computer. There's this idea of topological quantum computers, which I had read about. I think this might be the thing we need. So let's come to Microsoft. Let's build a quantum computer." So, so it started with that. And a story I've told a few times, but I'll repeat it anyway, is, he noticed in my office a picture of me on the summit of Mont Blanc, which is a mountain on this French-Swiss border. And he said, "I see you're a mountaineer, so you should come to Microsoft and we'll build a quantum computer and we'll climb Mount Rainier together." And so, we did climb Mount Rainier together. We did start working on the quantum computer, but, it's been 20 years and we made a lot of progress. We've learned it's a harder problem than we thought when we first started out, but we've also learned a lot of amazing things we never could have dreamed of at that time, and developed capabilities around device fabrication, like how you actually make these devices, simulation, so how you can predict and optimize the designs before you make them, measurement and data analysis, so many things that we couldn't have dreamed of at the time. We've learned and or developed, and that set us on our way. And we also have actually learned how to we've learned the human element of it, which is how to put together a team that's capable of doing something like this and working as a team. So there's a lot of things we learned along the way, and have made the journey both fun and also rewarding.
Amazing. I guess we live now in an era where we have like the classic quantum computer, and now we're talking about which is kind of crazy to think about. As a software engineer, I can't help but wonder what it would be like to develop software for a quantum computer. Speaking of software, Check this out. This is a custom website I built for us at Tuba Da Vinci in about 20 minutes using our sponsor, Odoo. Odoo is an all-in-one business operations software that offers a range of applications from CRM, sales, marketing, HR, accounting, inventory, point of sales, and even custom websites. Best of all, your first application is free for life, including unlimited hosting and support and a custom domain for 1 year. Here's my site so far, but I want to make a few changes. First, I don't like how big these video cards are. So let's shrink them down. And let's add a border radius for a nice, clean look. And let's update this image for technology while we're at it. Finally, let's add a contact us menu button and page so future sponsors and viewers can write to us. And since you're on the Odoo platform, user data like this can go straight into your own CRM platform for sales, consulting, or following up. So whether you're trying to start a new e-commerce business, sell courses, advertise your company, or anything else, don't let technology be the thing holding you back, and get started with Odoo today. You can get started for free with a website, and if your business takes off, you can just keep adding more features as you need it. Use our links in the description for the best deal. Huge thanks to Odoo and you. Now back to the show. So compared to a traditional quantum computer, tell me about the topological quantum computer and what makes this different and like the value that it provides.
Yeah, great question. So, from the earliest days of quantum computing, people have generally had different ideas about how to make a quantum computer. What should the underlying hardware look like? I think with classical computers now, we're on a pretty well-defined trajectory that Moore's law has been proving out Moore's law over decades. In the early days, classical computers were, I'm just going to say a little bit about the history of classical computers just to draw the analogy. In the early days, people made classical computers with vacuum tubes. The transistor hadn't yet been invented. We didn't really understand the properties of silicon or other semiconductors that well. Over time, we did learn those things. We discovered a lot of semiconductor physics, properties of silicon, how to understand and make devices. The transistor was invented, and then the integrated circuit, and we've been off and running. Since the earliest days of quantum computing, people have had different thoughts of what would be the right way. People have done lots of experiments at that point, testing out and probing quantum mechanics in various kinds of trapped atoms and ions. So you can take individual atoms or individual ions and trap them either in electric fields or laser beams, and use some property, usually the nuclear spin of those ions or neutral atoms, as your basic qubit. So ordinary computer has a bit, which is a 0 or 1. Quantum computer has what's called a qubit as the fundamental unit of information, and that can be what's called a quantum superposition of 0 and 1. So it can be kind of a little bit of both 0 and 1. It's not an analog computer where you get a continuous number that could be 0.3 or something. It's still 0 or 1, but you can have a quantum mechanical superposition like Schrodinger's cat being both dead and alive. And for the most part, almost all ideas around quantum computing have involved very different technologies and very different just physical manifestations than classical computers, with one exception, which is that Intel and HRL, for instance, have been making qubits using silicon processes very similar to what's used for classical microprocessors. But almost all the others involve either superconducting materials or trapped ions or neutral atoms. We took a different approach. Our approach was let's find a material that's just the right properties for quantum information. And for quantum information, for classical information, that turned out to be silicon transistors and integrated circuits. We moved away from vacuum tubes. And the fundamental property of quantum information that is so challenging is that it's very delicate. It's very, very delicate because not only do you not want your 0 to flip to a 1, but if you have one of these complicated superpositions of 0 and 1, you want it to be just the right kind of superposition. And so there's different kinds of error processes. And so the topological quantum computer is based on the concept that there are certain states of matter that have just the right properties that you can kind of protect that information. And I actually have a little prop here that I put together. You can see this is a Möbius band. I just took a piece of tape and kind of twisted it and glued it together. And what you can see is I can stretch this, pull on it, do whatever, and actually the number of twists doesn't change, right? You can do a lot. So, and if you think about that, the analogy there is you have a quantum state that similarly has a twist in it like this, and the presence or absence of a twist, uh, you might perturb that quantum state in various ways. The environment, there might be electromagnetic radiation, but it doesn't actually spoil the information. So there's certain types of information. That's what topology is. This is an example of topology, which is the number of twists in this band. Topology is very robust against, by definition, almost as robust against very small perturbations. And so the idea is, that you find quantum states that have this kind of property and encode information in basically these twists in quantum states. That's the topological. That's what a topological quantum computer does. And the catch is you have to find those states. You have to find a type of material that naturally wants to have states that have these kinds of properties in it, and that involves a lot of solid state physics and engineering, materials science and engineering to make those states of matter. Yeah.
Tell us a little bit about Majorana and like what happened there, and nanowire and everything else that goes into the
Yeah.
approach here.
Yeah. So the idea is that you take the way we're going to make the right state of matter is actually by taking a hybrid material. Okay. You could take another approach. You might have said, let's just get one fell swoop, we find some material somewhere in the universe that just has the right properties, that naturally its ground state, that its lowest energy states are naturally have these kinds of twists in them that you can manipulate. We instead said, let's make a hybrid material. Let's take a semiconductor and a superconductor and form that hybrid by putting them together. And if you put them together in the right way, and the interface is clean enough, then it turns out the semiconductor kind of inherits some of the properties of the superconductor, and you end up with something that's more than the sum of its parts, that actually you get the best of both worlds, because the semiconductor has important properties, most of which have to do with how tunable it is. You apply electric fields, you can change the density, and that's how semiconductors get used for on-off switches, because you can change their number of carriers they have by applying fields. The superconductor has this amazing property that the electrons form pairs that are called Cooper pairs. And that's how you get electricity running through the superconductor without any energy loss, because those Cooper pairs, their wave functions kind of line up very rigidly. And that rigidity is what enables them to carry these currents. You put this together and you get both of those properties together, as well as some others. If that hybrid material, under the right conditions, so we have to cool it down to really low temperatures, very close to absolute zero, and we have to apply a big magnetic field, but under the right conditions. So this state of matter is not just grown, it's also tuned. We think of that, we actually are familiar with that. Like ice doesn't occur in places that are very warm. Ice doesn't occur naturally, right? You actually have to, cool stuff down. You have to do something active in order to get ice. You similarly here have to not just cool it down, but apply a big magnetic field in order to get this new state of matter that has these topological properties. So it was a combination of, we got to figure out how to grow and pattern in the right way these materials, combinations of materials, make sure that we get the best of both worlds rather than the worst of both worlds, and then tune it into the right conditions so we get the state of matter that we want.
So, okay, I was kind of hoping you guys had figured out like room temperature superconductors, but no, we still have to cool
I know.
them. And
Yeah.
okay, that'll be the next.
That's next.
That'll be the
That's
next.
next. Like we're definitely working. Well, funny thing is, so we'd love to have room temperature superconductors, right? How are you going to get that? Well, you could trial and error. You could have some intuition. How are we going to get room temperature superconductors? Or, you could do
Use
a high
quantum
throughput.
computer.
Use a quantum computer. You want to do some high throughput simulations simulate lots and lots of materials, find some promising ones, then figure out how to grow them, then measure them, right? Well, we can't really do those. We cannot do the kinds of simulations that would tell you whether something's going to be a room temperature superconductor or not on a classical computer. But a quantum computer would be perfect for that. I mean, that's like the killer app of a quantum computer, actually. So, I think you were joking, but I'm serious. Like that's what we would do with a quantum computer. Like, right, that would be the thing I'd be almost most excited about using a quantum computer for.
So let's kind of switch gears for a minute. We'll come back to some of the technical stuff, because there's so many questions, and it's just so fascinating. But we've kind of touched on a little bit about the potential applications, which really are
Yeah.
interesting. Now, I
Yeah.
think most people think this new computer, I have class computers and quantum, they're thinking like, I want to play video game.
Yeah.
The use cases are not quite what people are thinking, probably, but
Right.
it's really fascinating. You mentioned material science. I think material science, it would be just an
Mm.
absolute game changer.
Yeah.
There's
Yeah.
so much. I mean, we've identified our advancement as a civilization by materials, right? It's the Bronze Age, it's the
Yeah.
Iron
Yeah.
Age. It's foundational to how we build everything around us, and it's always been a limiting factor in how quickly we could add a little bit more carbon to make this steel stronger or vice versa.
Yeah.
So that's a good example. Biology seems equally brilliant. I mean, just the complexity of the human body, drug therapies, genomes, like there's so many considerations there. Chemistry is another really good one, right? I can think of what are some, if this were like, let's say in the next couple of years, you guys nail it. We go from 8 qubits to thousands to hundreds of
Yeah.
thousands to millions or
Yeah.
something, and this becomes just a part of our culture.
Yeah.
Where do you see the next breakthroughs really coming from quantum computing?
Okay, so number one, you made a really important point that I just want to like hammer a little bit more, which is um, quantum computers aren't actually good for every single thing, right? It's not because I think sometimes people think, well, quantum computers is like a classical computer, but it's like 10 times faster or a million times faster. It's actually not, right? There are many things that a quantum computer just won't be very good at, or it'll be worse than a classical computer, right? Classical computers are fantastic at a lot of things. Quantum computers are bad at some of those things. But there's some things that quantum computers are just amazing, and not amazing like 100 times faster, but amazing in classical computer would never solve it if you had the entire age of the universe to work on it, and a quantum computer can. And first and foremost among those is any simulating anything having to do with quantum mechanics. So, like you said, it's chemistry, it's materials, it's some aspects of biology. So, let me give you some examples. We would love to have some catalysts that could help with carbon capture right out of the atom. We know there's a lot of carbon in the atmosphere. If we have catalysts to capture carbon out of the, help us capture carbon out of the atmosphere without using up a lot of energy, because capturing gases actually takes and turning them through some chemical reaction into something that you can then bury in the ground or use for something else. That actually costs a lot of energy, right? So you want some catalyst that enables you to do this without spending a lot of energy, right? That seems like a big one to me, right? Um, Along those lines, nitrogen fixation. So again, we pull nitrogen. Most of the atmosphere, most of the air that we breathe is nitrogen, right? We pull that nitrogen out of the air and put it into fertilizers. It's really essential for growing the food that we eat. It's actually not a very efficient process. There are catalysts involved that help it, but it's a 100-year-old process. We haven't had we've had improvements, but not major breakthroughs. It's a Haber-Bosch process, 100-year-old process. Um, it's actually quite inefficient. It's very costly energy-wise, but we know like bacteria do it way more efficiently, but not
Right.
scalably, right? So that's not an answer either. Is not just have a lot more bacteria, but it does give us a hint that there might be better ways of doing this. And so if we find catalysts through simulation that can help us with nitrogen fixation, I think that's a really big deal because we do need to feed the planet, right? So
Yeah.
those are two big ones. Microplastics. We'd love to have things that can break down microplastics. So again, I look around and people sometimes think, well, oh, it's not going to help with like social media, and it's not going to help with gaming. Oh, it's just some niche thing that you're only going to worry about for like chemistry and materials. And then you say, well, yeah, but 96% of all manufactured goods involve chemistry and materials. So that's like everything. So, in that sense, for me at least, it's really exciting.
Yeah, it's one of those things. A lot of people don't realize how impactful scientific breakthroughs can be
Yeah,
until suddenly it enters their lives, and then it's hard to imagine. Like vulcanized rubber. Think about that.
yeah,
Think about our world without vulcanized rubber. We'd be
yeah,
driving 25 miles an hour on wooden wheels, and it's just incredible what that
yeah,
does. Now, another example, I had chatted with 3M a couple years ago. We made a video about this breakthrough they made for hydrogen electrolysis using iridium. So they again, this
yeah,
probably took 10 years, and they came up with this one brilliant catalyst,
yeah,
iridium-based catalyst that was really great and way more efficient. But iridium is very, very scarce on Earth.
yeah,
Very hard to imagine building that up.
yeah,
Imagine if we could get the potential benefits, the efficiency gains
yeah,
of some other more, run-of-the-mill material that's more commonly available in the Earth's
Yeah.
crust and have those benefits. I mean, that would change things in major ways. Um, so really, it sounds like we could potentially speed up the process of finding these breakthroughs, making these improvements, iterating on materials, and get to simulation answers more quickly.
That's right. I mean, I think in some sense the story of the last 50 years, in my mind, has been a story of having more and more computing power and turning that computing power into increased productivities and efficiencies, like across all kinds of industries. And where I think if you look at areas where it hasn't maybe had as much impact as it could, in often it's cases where you just can't, even though we have a lot of computing power, we can't simulate certain things. And among those things are there's certain kinds of chemical reactions, certain kinds of materials, certain kinds of properties that are simply very because quantum mechanics is so important for them that we just can't simulate very well. We can after the fact simulate. So you discover something and you want to understand, well, why did that work? You can do simulations that kind of explain, okay, here's the reaction pathway, this is why that worked, but not quite predictive enough or not accurate enough for you to trust the predictions that well. If we get to a stage as soon as possible, I hope that we have predictive simulations of chemistry and materials in a regime where the quantum mechanics is very important, which generally, like general rule, is anything involving transition metals fits into that. So we talk about high temperature superconductors. Well, they're based on copper. We talk about like hemoglobin is iron, right? You just talked about iridium. There are many within the transition metals. That's a part of the periodic table where the compounds, the materials, and the chemicals that they're in often have a lot of quantum mechanics at the heart of their behavior and are very hard to simulate as a result.
I'll tell you, even from when I was in college, and I remember taking in engineering school, taking quantum mechanics and thinking, this seems like such an abstract, wildly, and now it feels like even now, the quantum computer is not quite here yet. It's coming. We're on the cusp, but quantum mechanics is now kind of in the psyche of civilization. We're all talking about it. It's kind of
Yeah.
central. One really beautiful sentiment I've heard somebody express is, trying to model the world with classical computers is always going to be tough because you're trying to, you're modeling the quantum world in these like, binary bits. And the quantum computer revolution will be a game changer because now we're modeling the quantum world with a quantum computer. And so it's just so much better at handling some of
Yeah.
those interactions and stuff. Now, for climate change, there's a huge slew of benefits, right? We've talked a little bit about just climate modeling and predictions, which are, I mean, the number of variables. If you start trying to predict the number of variables in a system, it becomes unimaginable to try to model some of this stuff, and it becomes a lot easier.
Let me just take an opportunity to jump in there and say, so again, I don't think quantum computers are going to be great for every single thing. So there's going to be aspects of climate modeling where quantum computers aren't particularly helpful, maybe like big data type stuff. So quantum computers, we don't expect to be great, at least initially, for big data because it's expensive and slow to get a lot of data into a quantum computer, and they can't hold vast amounts of classical data. What they can do is they can do a lot of compute on a small amount of data. I mean, the classic example of that is, like I said, like code breaking, where you have some code like RSA 2048, you have some key that you want to factor or crack. You have to do a lot of compute, but the problem statement is small. Now, there are aspects of the climate and the chemical reactions that are involved where quantum mechanics is really important. And I think that quantum computers could make a big deal in terms of our understanding of some of those things. And then there are going to be aspects that I think that AI is going to be really useful for, and classical high performance computing. So I think that we we should view this as it's part of the set of tools that we have. All multiple of which are becoming exciting around the same time. We've got like all this classical HPC, these big data centers. We've got AI and the ability of many of these models to generative AI to enable us to understand big data sets and make sense out of large data and extrapolate from it. And then we've got quantum computing to help us understand things that we really just can't understand any other way, and which often are at the heart of like the really hard problems that we care about a lot.
Yeah, so that's really well said. So Majorana 1 has 8 qubits, right? So what are, I mean, and that's pretty incredible and remarkable. Now, as I'm sure you guys are hard at work on how do you make that 100? How do you make it 1,000? What is
Yeah,
the challenge there? Like, walk us through a little bit about the R&D that goes into scaling that number up from here.
it's a great question because the world has gone through that with classical computing, right? And you might want to compare the history. Like, how does this compare to classical computing and all the steps you had to go through there? So if you think about classical computing, they went, the first transistor was this, point contact transistor, and then, bipolar junctions, bipolar transistor, and then eventually got to MOSFETs and, CMOS and so on, and the integrated circuits. So the path you'll take will depend on the particular technology you're looking at. So, there's things happening with ion traps and so on. I can only speak to our approach. So just to be clear, with Majorana 1 and the topological approach, I got to emphasize that there's lots of exciting stuff happening in this field with other approaches. And I think there's going to be, I should also mention photonic quantum computers, defects in silicon. So there are a number of really exciting technologies. I think it would be fantastic, and I wouldn't be surprised at all if multiple of these turn out to pan out and be useful for particular different applications. One or another might be more convenient at a given problem size, or might be less expensive for certain types of problems. What I know the best is the topological roadmap, and so there I can say, there are we really it's two main axes. One axis is just more qubits, more complexity, and as you increase the number of qubits, there's two things that really come into at play, and I'll explain them. The other axis is just better qubits. Okay, and when I think about better qubits, it really comes down to, we discussed briefly, the twisting of the wave function, of the quantum mechanical wave function, is this very rigid thing that protects the information. But I can eventually tear this thing open, right, and untwist it. And that the analog for a topological quantum computer is something called the topological gap. It's an energy gap. It's an energy scale. The larger you make that gap, the more stable it is, and the better your qubits are. And that's a fundamental material property. So there is material development that we're doing. So, right now, everything we're doing is based on a semiconductor called indium arsenide. So it's a compound semiconductor involving indium and arsenic, and the superconductor is aluminum. We can make changes to that material stack. Now that we have something that we understand reasonably well, we can tweak it. And as you tweak it, you can make that topological gap better, bigger. And the power of the superpower of the topological approach is small improvements in that energy gap lead to big improvements in qubit performance. So there's a material development, that's one axis. The other is more qubits, more complex devices. And as you go up in scale with more complex devices, you actually rely upon those improvements in qubit quality, because the more qubits you have, well, the more chance of crosstalk, the more sources of noise, a little more heating you're going to have, because all of this is done at these very cold temperatures, in these special kinds of refrigerators called dilution refrigerators, which are really the coldest places in the entire known universe. That's how cold they are. 50 millikelvin is, more than 10 times colder, more than 20 times colder than interstellar space if it's 100 millikelvin. So the interstellar space is like almost a little less than 3 Kelvin, and we're talking about 100 millikelvin. We've got to make the qubits better as we make the systems more complex. So that's one piece. And as you go to more qubits, a particular difficulty that arises as you go to more qubits is, how do you get that information in and out? Right? At the end of the day, we want the answer to some problem, which is a string of zeros and ones, right? But what you've got inside of your quantum computer is a quantum state. And some unique features are, if you take like, your cell phone or something, it's got, or the computers we're recording this on, they've got like billions of transistors on that processor, but a few thousand control lines. So the number of lines in and out, the number of pins on that chip, is way smaller than the number of transistors. That's not true for a quantum computer. Every single qubit has to have a control line, basically. And so
Interesting.
you have to figure out what you might say is an extremely complex. I'm going to say it in a way that makes it trivializes it, but you'll realize that I'm kind of joking. You have a very complex wiring problem to solve, right? How do I wire up a million qubits? Now, it's obviously not just a wiring problem. It's a fundamental problem of how I get this information in and out. Okay. The topological qubits, like the beauty of it is the kinds of operations I do are primarily from the beginning digital, right? It's, if what I'm working with is number of twists, then the operations also are like twisting, untwisting, that kind of stuff is also very digital. So the benefit of that approach is that everything is done basically through a control that's highly digital. And because that's a serious problem you have to solve is how to get the information in, which is the information of what is the algorithm you're doing. But that brings along with it a whole bunch of challenges. And so a major part of scale up is as you scale up, your control system has got to scale with it in such a way that you can still preserve the coherence of your qubits and so on. So there's actually a lot of, I would say, classical electrical engineering and
Right.
circuit design, classical circuit design that has to keep pace with increasing the number of qubits. And then there's similarly the flip side, which you got to read all this information out. And so there's a digital signal processing that all this information that initially is analog and then has to become digital to come out. So, and that then has knock-on problems associated with keeping the whole thing cold and shielded and so on. So there's a big system engineering problem you have to solve, which is to keep pace as you make these devices larger, keep pace with, of course, you have to have the yields being very high and so on, because you can't have broken qubits when you have, qubits that are sitting in, or you need to have very few of these broken qubits. If you have a transistor or something that's broke, one transistor is broken on your processor, there are lots of workarounds. There's many fewer workarounds, with qubits. So there's the challenges having to do with scaling up, or one for us at least is on the material side. Keep getting that topological gap larger and larger to make them better and better, and then there's a scaling problem.
Wow, that was fantastic. Interesting. So yeah, even if we have a billion transistors, we don't actually need. There's a instruction set, and actually the outputs are limited in a way that's different. Than I had never thought about that.
There's a lot of fan out and fan in, right? There's
Yeah.
like you can set a limit of instructions they can fan out on a classical processor, and you don't have that with qubits.
Interesting. Wow. Okay. We've talked a little bit about the security ramifications of quantum computers, and I think I kind of understand it, but and I'm sure you probably get this question more often. But do you have a good analogy or a way to kind of visualize or conceptually understand what it is about the qubit and like the quantum computer inherently that makes it able to, I mean, serially try, let's say, for example, you're trying to break a password or something like that. And to your point, if you have a classic computer, you're going to try 0001, and you're just going to try every permutation, it would take you longer than you have time on this universe, than over 5 billion years. What, like, and in a simple way that like people could kind of visualize themselves, what is it about the quantum computer that is able to do that so easily?
Okay, I'll try. It's going to be a little technical, but I'll give it a try. Okay.
No, that's fine.
Okay. Okay. Well, okay, but it requires a bunch of steps. So I'm just giving you fair warning. So, first of all, if you think about RSA, for instance, the basic operating principle is that it's really hard to factor big numbers. So if I take like two prime numbers, 3 and 7, and if I give you 3 and 7, it's easy to multiply them together and figure out the 21. If I gave you 21, it's actually a little bit harder to figure out that 3 and 7 are the prime factors. Okay. Now with 21, you can exhaustively try and you'll get there. But with, if I give you a very large number, it's not that easy to find. I mean, obviously, if it's even, you'll say, oh, two divides it. But if I give you a very large number and it's not divisible by 2, 3, 5, 7, some easy ones, it's hard to find factors of it, right? So RSA is based on the idea that you can publicly give everyone your public key, which is the product of those two numbers, and they can use that to encrypt information. And I alone know what the two factors are, that multiply together to give that, which I need to decrypt the information. So it's sort of almost a one-way street, right? And so then you have to say, well, how do I figure out, factors of these numbers? And it turns out that prime numbers have these amazing properties having to do with periodicities, because as you take prime numbers, you take numbers and you take them to higher powers and so on, the remainders end up satisfying kind of a periodicity process. Okay, as I look at prime numbers and take them to higher powers and multiply them together. So it comes down then to I've got some function. I know it's got some periodicity. I need to figure out what the periodicity of it is. Okay, that's among other things, you use Fourier transforms to figure stuff out like that. Okay, but this in this case is discrete because it's not some continuous, but it's some kind of periodicity having to do with multiplying prime numbers together. Okay, so under those circumstances, quantum computers turns out are really good at finding periodicities. Not necessarily giving you the full Fourier transform, but finding some underlying periodicities. Quantum computers are really good at. And so it's the ability to find underlying periodic structure inside of some discrete data, like a string of numbers that you get out of multiplying stuff together, is is a superpower of quantum computers. Okay, so that's part one. Okay. Okay, which is some basic. I mean, another way of saying is there's some basic number theory having to do with prime numbers and multiplying them together, and it turns out that it's hard. It's hard to do in one direction and easy to do in the other direction. That enables you to encrypt information and hard to decrypt if you don't sort of know the key. Then I gave you a statement: quantum computers are good at this. Now, why are quantum computers good at this? Well, this comes down to something called superposition. Which you alluded to with like trying all these different things. So Richard Feynman used to say, the key to understanding quantum mechanics is if you understand the two-slit experiment, then you understand quantum mechanics. Now, he also said, well, but don't worry, nobody understands it. So
Yeah,
fair
I remember
warning
that
on
part.
that one. Yeah, fair warning on that one. But anyway, so maybe we don't understand it, but we made peace with it. So the idea is you have a screen, it's got two slits in it. You shine coherent light like from a laser. And if one slit is shut, you just see, you see some pattern. It's most intense in the middle, and then the intensity falls off to the side. There's actually some oscillation, some ripples in it, depending on the size of the slit. But if you make the slit narrow enough, you just see some kind of, fairly smooth pattern. You close that slit, you open the other slit, you see a different pattern, right? It's kind of peaked more behind the other slit. You now, suppose you open the two slits, what you see is not the sum of those two things. They actually interfere with each other, and you see something periodic, which is strongest in the middle and actually goes to zero in various places, because in some places, because light is actually a wave, and those waves in some places interfere constructively because both waves are peaked. In other places, they interfere destructively because one is at its peak and the other is at its trough. And so that interference effect picks out actually a very natural periodicity. And actually from that interference effect, you can actually tell the wavelength. You can either tell the wavelength of the light, or if you know the wavelength of light, the distance between the slits. So there's a lot of underlying that the interference effect allows you to extract something about periodicity. And Shor's algorithm is an extremely creative and really brilliant way of using that aspect of quantum mechanics to extract out the exact right periodicity that you need to solve this cryptography problem.
That's well said. Interesting. Okay. Yeah. I from Feynman, I always remember the key to understanding quantum mechanics is you don't understand quantum mechanics. That part I was
Right.
very at peace with from a very early
Yeah.
early point. But that's okay. Um, so is there anything else you want to actually Israel? You have any questions you want to ask Israel?
Well, first of all, it's great having you here. It's great to meet you. An honor. And second, yeah, I do have. Well, obviously, I have many questions, but I think one of the questions that most of our viewers probably have regarding quantum computers is, they always wonder if are we going to have quantum computers at home, right? And kind of touching back on what you were talking about, that quantum computers are good for solving some problems, but not for solving others. So, like, are there any specific use cases that you might envision for a quantum computer at home or the office? And that's one question. And I also had another question about AI model training, actually, because the way I understand it, quantum computers are good at optimization problems. And the way I understand, for example, large language model training, it's basically a large optimization problem. So I'm thinking, would it be possible to have, for example, a quantum computer at home that we could use to train our own models, and then have a classical computer to run those models? Because I assume that the quantum computer wouldn't be good at running the model, right?
Okay, great. So two separate questions. Let me take them in order. So first of all, I don't think, I mean, I don't think at least the earliest quantum computers would be in people's homes or offices. I think they'll be in the cloud, right? We're going to put them in data centers. And I feel like the workflow is often going to be a very hybrid workflow where you have classical high performance computing, you have AI, you have quantum computing, and you'll be using some combination of those three things. And that's very natural in a data center. Data centers right now, we have CPUs, we have GPUs, we're going to have QPUs there too, quantum processing units. So I think that, honestly, to the end user, I don't think to the end user the end user shouldn't even necessarily realize what's being used when. An end user cares about what's the solution to the problem that I care about and how that problem gets divided up between the QPUs, GPUs, CPUs. I don't think end users should worry about. And so I think this is, at least in the early stages, this is all something that is going to be in the cloud. You'll interact with the same way you interact with anything else happening in the cloud. Now, as we were joking earlier, we're going to use a quantum computer to find much higher temperature superconductors, to find topological phases that are extremely stable at room temperature, and then maybe you wouldn't need the extreme conditions that we currently need. So the other thing is, I said, there are the dilution refrigerators. We use special kinds of refrigerators. So, data centers right now have this massive cooling problem to keep all these server racks cold. A quantum computer, like once you put those in the data center, it's even more complicated cryogenics because it involves liquid helium and cooling down to these millikelvin temperatures. So that, again, is definitely something you want in a special facility. When we make quantum computers that can operate at room temperature, then it's a different story. And maybe you can distribute these, put these on site in various places. But, I think, for the near future at least, I would say this is something you should plan on interacting with primarily through the cloud. We are, on the other hand, doing deployments, across the industry. There are deployments of quantum computers on site to various companies and research institutes, and I think that is particularly important in this stage because researchers, graduate students, and so on, even college students, it's really helpful to be able to run these things backwards and forwards and goose them every which way and really treat them as a research tool and play around with them. And that's really helpful when it's it's on site. But again, these are research institutes and universities or R&D departments of big companies where they can maintain these the special conditions that you need to run quantum computers. So that's your first question. I hope that answers it. We can follow up if not.
Absolutely.
Then to your second question, I think that one of the exciting directions. So quantum computers, again, I don't think in the early stages are going to be great for big data. So these AI models, like large language models that have billions or tens of billions of parameters in them, that's big data. That's hard to even formulate and get a problem like that into a quantum computer. Okay. On the other hand, you could use a quantum computer to generate, what's often called synthetic training data. So if you want to train your AI model to solve quantum problems, you need high quality data that's generated where you really understand, what that data is. And so, particularly if you have like labeled training data, you want to have that, and you can use a quantum computer to generate that data. So I think a quantum computer as a way to generate synthetic training data for AI models that are useful for science and engineering, that to me seems, like a really exciting application. And a very natural place where quantum computing and AI come together.
Absolutely. I completely agree. And just one very quick question. Sorry, Ricky. It's just something that I have on my mind. From your perspective, how important are true random numbers? Because I think that's one of the applications for quantum computers, that they can actually generate true random numbers.
Well, true random numbers are actually useful for one-time pads, for encoding information. So if you have a good random number, then a great way to set information is if if both sides have that pad, you can just encode it with that truly random number. If there happens to be some underlying structure, then it is not provably secure. So that's one potential application, I think, and of course you could use a quantum communication channel to distribute that, because there are ways through quantum communication channels that in principle are provably secure that you can use to send things like that. And so you want to link up data centers, maybe you send those one-time pads, those keys between data centers over a quantum communication channel, as an example. There are also many simulations that we run, okay, which it really is important that it be random. I mean, to take another example, it is actually relatively important that the roulette wheel lands on a random number, right? Otherwise, the house might lose a lot of money if it's not quite random. So, you could imagine quantum computers give you good random numbers for things like that. But on a more serious note, there are lots of simulations we run where we do require either random seeds or actually like a steady supply of random numbers. And if it's not quite random, then actually it does throw off the results of your simulation. So there are a number of potential applications of truly random numbers. I think there's lots of other applications of a quantum computer. Like I said, as we discussed earlier, 96% of all manufactured goods rely on materials and chemistry. So
Yeah.
that's much less niche than provably random numbers.
Yeah. I love
Very
the random number question is interesting because I don't think people realize how hard that is for a classical computer to do. In fact, it's if you hit that generate button enough, you'll find the pattern. It's just a matter of time.
Yeah.
It kind of breaks down for me. That was one of those moments when you realize that people are so good at things and the computer is not, or vice versa. And quantum is another level to that. It's like another layer of the onion that you could
Yeah,
look at and
yeah.
say, wow, that's such an easy. Like my boys, my sons could give you random numbers all day and you'll never crack it. Like they could do that day and night. But this is it's a great way to look at, and I love what you said about the toolkit, right? This is another tool in the toolkit. Right now we have CPUs and GPUs. Obviously GPUs are much better for matrix math and some of the AI
Yeah.
stuff. And then we'll have QPUs, and as a user you might just log into Azure or something and just
Yeah.
say, I need to run this kind of a model or this kind
I
of
hope it's
simulation and
Azure.
do
Yeah,
this.
I hope it's Azure.
Yeah.
Yeah.
I've heard there's some other ones out there.
I guess
I
I'm not
couldn't
sure.
name them,
Yeah.
but exactly, and the end result is you just get compute. You
Yeah.
might not even really need to know.
Yeah.
Ultimately,
Yeah.
I mean, for a while it's going to be all the rave. You're going to have, Microsoft side is going to be littered with like quantum computer. It's just like AI is today. But eventually it'll just settle into just the norm, and it'll just be what we
Yeah.
use as scientists and engineers to build stuff. Now,
Yeah.
we were at CERN last week, a couple weeks ago, and I was
Cool.
just blown away. Some of this particle physics and quantum mechanics, it's in a lot of ways I'm seeing it might be the greatest marrying of engineering and science I've ever seen, because you really got to bring those two things together to get some of this stuff out. I mean, if you want to get out of the lab and actually have something you can hold in your hand, like it's an incredible area of study. And what I love about this, and the reason why we're making this story, if I had to break it down to one reason, is
Mhm.
in my mind I've always I've always hoped that there's a way we can fund great research more easily.
Mhm.
And when I hear about companies like Microsoft doing this,
Yeah.
obviously, I mean, the benefits to Microsoft are huge, right? Like we just talked
Yeah.
about. If you have the cloud that has the quantum computer behind there, it's going to be great for business. But for 20 years, you guys have been investing in this thing.
Yeah.
And it's really important, I think, going forward when companies do that. It's one of those key ways. Companies that have high level of success and wisdom can go and recruit people like you to work on these problems. I think that's kind of what's always been missing, because public funding is so hit or miss. It's the next administration. It's cut. It's very difficult, and it's always what scientists have always told me. The hardest part is just getting the funding to keep doing my research. So, what Microsoft is doing here is hopefully the business model of what you do. Like when you get to a certain level, yes, you dividend buybacks, and there's other financial things that you do. But one of the things that you should really do is push the envelope, and it's an amazing part of the Microsoft story that I find freaking fascinating, and I hope it's kind of the beginning of a new paradigm of how we do it.
Thank you very much. I think I thought about that a lot too. And if you think about like why we as a society, or how did we as a civilization end up with the idea of a corporation? Well, I think we ended up with a corporation because we want there to exist something that makes a profit by solving problems that are important to humanity,
Yes,
right?
yes,
Right? I mean, that's the whole goal is that solving problems that humanity relies on in a way that turns a profit. And I think maybe in some ways the extreme case of that is the hyperscalers like Microsoft, which are unique in human history, more or less, and really have the ability to do that.
yeah, amazing. We're probably right about an hour. thank you so much for your time. It was incredibly enlightening, and I know
And
you're
oh,
busy,
sorry,
so
if I could just add like one more little coda
sure,
to what I just said,
absolutely,
which is just it's the 50th anniversary of Microsoft. Actually, the 50th this year, and
really,
actually, yeah. So April 4th was officially the 50th anniversary. I think that's when Microsoft was incorporated. And as I was thinking back on that, we've our quantum program, like you said, we've been going at this for a while. We've had the support of actually all three CEOs of Microsoft. We've had Bill Gates, Steve Ballmer, and now Satya Nadella all supporting the quantum program. So I think that shows the sense in which companies like this can do. Microsoft has the ability to do bold and difficult things, and I
yeah,
think that's unique and special.
amazing. I didn't realize it was, wow, 50 years,
Years.
incredible. Well, Chetan, thank you so much. Really, really, an absolute pleasure to chat with
Yeah.
you, and hopefully there's some cool stuff in the future we can chat about and catch up soon. But I really appreciate you taking the time. It means a lot to us, and have a great rest of your week. Yeah,
Yeah. Thanks. You too. Really appreciate it. It was fun talking.
thanks so much.